Welcome back, Virtual Algebra 2. This is section 10.6. This will be the last section in the chapter on probability that we work on together. This is about dependent events or conditional probability. And it's a bit confusing. There are lots of different approaches, and the book really doesn't discuss much the relationships between them. So I'd like to hopefully highlight that a bit to help clear things up for you. Because really, it is kind of one subject, and all the different problems we do in this section are related, and it's nice to see the connections. So the main idea, though, is always going to be that there's one event, and whether or not it happens affects the other event and the probability of that second event. Some of the strategies we're going to use are Venn diagrams, which I know you're familiar with, tree diagrams, which we've also seen together, something I call adjusting the possibilities, and it sounds complicated, but it's really sort of common sense, and I'll walk you through that in a minute. And then this new wacky one, the conditional probability formula. And the first time I saw that, I had no idea why it was true. Hopefully I can motivate that for you today. Alright, so we're going to approach this by just working through a series of examples. The first one is example 1 from the section in your book. In that example, we have 50 band members and 20 student council members. And it so happens that 5 of those student council members are also in the band. And a Venn diagram is a perfect choice for this kind of problem. You can see it here. And the 5 there in the middle represents the fact that 5 of the people in student council are also in the band. The question says, if we select a student at random from the student council, what is the probability that they're in the band? Well, with the Venn diagram, it's really visual and easy to see that of the 20 student council members, 5 of them are in the band, so it's 5 out of 20, or 1 out of 4, or 25%. But there's another way to look at this, and that is the so-called conditional probability formula. And that's what's boxed in red here. Okay, first thing we have to do is we have to get used to this notation. This first part here is read as the probability of B given A. What does that mean? Given means assuming that it has happened. Okay, so we're looking for the probability that B will happen if we assume that A has already happened. And the formula tells us that that's equal to the probability that A and B will happen divided by the probability that A will happen. Now that should, I hope, be a little bit mysterious for now. I'm going to try to clear it up if I can. So in this case, B is being in the band and A is being in the student council. So what's the probability that you're in the band given that we know you're already in the student council? Well, according to the formula, it's the probability that you're in both divided by the probability that you're in the student council. Well, the probability that you're in both, you have to be one of those 5 students out of the 65 that are in the middle of the Venn diagram. So 5 out of 65. And what's the probability that you're in the student council at all? Well, that's pretty easy. There's 20 of you out of the 65 students. So 5 over 65 divided by 20 over 65, which is 5 over 20, 1 out of 4, 25%. What do you know? This crazy looking formula actually works. Again, if I just saw this, I probably wouldn't believe it, I probably wouldn't understand it, and so I hope in some further examples to make it less mysterious. But so far, this mysterious, weird thing, the conditional probability formula works. So let's look at some other examples and see how they relate to this one. Okay, in example 2 from your section 10.6, you have a bag with 12 marbles in it. 9 of them are red and 3 are green. And this is interesting because they want us to answer a question in 2 different ways. They want us to answer what is the probability of getting a red and then getting a green. But first, we're supposed to assume that after you draw the first marble, you put it back and scramble them up. That's part A. That's called with replacement. And the second, part B, we don't have replacement. That means after we pull out a marble, we don't put it back. We leave it out of the bag. Okay, so the first part, with replacement, this is just another example of independent events. Because finding a marble that's red the first time does not affect the chances of finding a marble that's green the second time as long as we put the marble back. Okay, so independent events with replacement. And the chances of getting a red, well, that's just 9 out of 12, which is 3 out of 4. And we put the marble back, so there's still 12, and then the chances of getting a green are 3 out of 12, or 1 out of 4. So when you have independent events, the chances of getting both is the product of the chances of each one. So it's 3/4 times 1/4, or 3 out of 16. So that part's just really the same as what we did in 10.5. Okay, in part B it gets interesting. What's the chances that we get a red and then a green if we don't put the first marble back? No replacement. This is definitely an instance of dependent events. Because if we get the red out, that's 9 out of 12, 3 out of 4, that's the same. But now, because we've taken one out, we've affected the next situation. So we have to adjust the possibilities. Okay? It's kind of common sense, but we can't forget to do that. What I mean is, there's still 3 green in there, but there's only 11 marbles to choose from, so our odds are slightly better than before of getting a green. Instead of 3 out of 12, it's now 3 out of 11. Okay, so after adjusting the possibilities, then again, we just do a multiplication. It's an and after all. And the chances of getting red times the chances of getting green are now 3/4 times 3/11, and it comes out to 9 over 44. Right, so if you find those as decimals, they're going to be slightly different, 3/16 and 9/44. You're going to have a slightly better chance in the second case, because you've reduced the number of red marbles in the bag. Alright, now I'd like to tie this into the conditional probability formula. It's a bit awkward, but I think it does help us to understand why that formula must be true. Okay, so I need to rewrite this last statement here, PR times PG equals 9 over 44. 9 over 44 is the probability of getting a red and a green, right? And we said that that was equal to the probability of getting a red, 3 over 4, times the probability of getting a green. But that probability of getting a green is really not just plain old probability of getting a green, right? Because it's the chances that we get a green given that we've already taken out a red. So it's really probability of G given R. Alright, so if we think about that equation there symbolically, and if we rearrange it, solving for that P of G given R, meaning we're going to divide both sides by P of R, we end up with this. The probability of G given R is the probability of R and G divided by the probability of R. And that is the conditional probability formula. So it's not hocus pocus, it's not magic. It's just basically like the inverted version of finding an and, right? When you find an and in probability, you multiply, and we've sort of messed it around and divided both sides by something, and this is the natural consequence. So just to show you that it works again, P of R and G we said was 9/44, and the probability of just getting a red is 3/4. Dividing fractions means multiplying by the reciprocal of the denominator, and what do you know? It comes out to 3/11, which is what we found by adjusting the possibilities. So, in this case, it was easy to just work through it kind of logically, adjusting the possibilities for the second pull without replacement. But that crazy conditional probability formula does work, and it is consistent with all the other probability math we've been doing. One last quick example. What's the chances of getting 2 aces in a row from a standard deck with no replacement? Well, there are 4 aces in the deck and 52 cards in the deck, so the chances of getting our first ace are 4 out of 52 or 1 out of 13. Now, looking for that second ace, we have to adjust our possibilities because we've taken a card out. Okay, so the chances of getting ace number 2, given that we've gotten ace number 1, are 3 out of 51, 3 aces left out of 51 cards left, which reduces to 1 out of 17. Okay, the chances of getting the first ace and the second ace are the chances of getting the first ace times the chances of getting the second ace given that we got the first ace. So the overall probability is 1 out of 221. We can invert this just like in the previous example to show once again that the conditional probability formula does work. Pause it and stare at this if you need to for a minute. See you in part 2.